Hello again. So in this session, we are going to do a dimensional analysis in the inertial subrange. So as you see, we did look at the characteristic scales, length scale and time scales in energy containing range. And also we did so for dissipation range by looking at the variables that are important in that range. And now I want to do the same analysis, but now for inertial subrange. So let's get started. Inertial subrange. So let's look at what are the important parameters or variables in the inertial subrange. So if you remember from previous lectures, if we plot the spectral flux and this is EK, spectral flux, we get something like this. So it was increasing because of production, and then in the inertial region, inertial subrange, it was kind of constant, then it decreased in the dissipation range. So based on this, we divided the flow into these three regions. KE for production range, KM, KD for dissipation range, and also we can define something for any range here, any, let's say, particular wave number, we just name it Km. That's for the inertial range. And also we know that this value here equals to the maximum is the total dissipation in the flow, or epsilon. Okay? So we know that epsilon k for Km, as you see here, is going to be a constant, and it's going to equal epsilon, where Km is between KD and KE, right? So if you remember it, we talked about it in the previous lecture here. And this spectral flux is just the minus of the integral from 0 to k of the Tk Td dk, okay? And here we showed that this total thing is going to be the total dissipation in the flow, which is epsilon, this value here. Okay, so now that we know this, let's which is the rate of dissipation here. You see it here, right? So in this range, we know that based on this equation, this can be the spectral flux, and based on this equation, we don't have that much. If we don't have that much tendency, then epsilon here is going to be just equal to that spectral flux there. Okay, so based on this, you just see that also we know that EKM what the EKM in the inertial subrange, as you see it here, which is this red line, or you can also look at it, say from here, this graph, or either this graph or this one, but maybe this one, yeah. So in the inertial subrange, which is around here, Km, this EKM is about 0 because we don't have any energy production. So this is, we know that in inertial subrange, this should be about 0. And so in this range, in this subrange, we don't have no energy production. No energy, we don't have any energy production. What does that mean? So this means that U square and L are not important in this range. So this is one thing that we get because these U square and L are from the large scale, and because we don't have any energy production, these two scales are not important in this inertial subrange. Also, we know that dkm also equals about 0 in this subrange. If you see, the only important thing here is energy transfer, and then the rest are just not important. So here dkm is also, as you see, is about 0 here. So in this range, the only thing, we don't have those. Dissipation and energy, we don't have neither dissipation nor energy production. So this means that nu, which is related to the dissipation, can be neglected since no dissipation in this range. No dissipation occurs in this range. Again, this is by assuming that separation of scales that we made in the at the beginning of this argument. So what does this mean? This means that E of k in this range should be a function of the only thing that remains here. What are the only remaining things? The only remaining things are k and epsilon. We know it's going to be a function of epsilon, and we also have k, and we don't have any other variables for this to kind of be a characteristic thing here. So we don't have nu, we don't have u, and we don't have l, unlike the other ranges. So here, for example, we had u, l, and here we had nu epsilon, but here we don't have dissipation. Dissipation is not that important in this range. So the only important things that remain are k, the wave number, and epsilon, the energy dissipation rate. So now, based on this, we can do a dimensional analysis to find the dependence of energy spectrum to k and epsilon. So Ek, the units of that is L cubed t to the minus 2. The unit of k is wave number is L to minus 1. And the unit of energy dissipation rate is u square over time. It's the rate, so it's going to be L square t to the minus 2. T to the minus 3. So now, based on this, we can do a simple dimensional analysis. So let's say Ek is C, which C is a constant, then k to the power alpha, and epsilon to power beta. So let's do a dimension analysis. The dimension of the left-hand side should equal to the dimension of the right-hand side. So we have L cubed t to the minus 2 equals to C is a dimensionless number, K is L to the minus 1, so it's going to be L to the minus alpha times L squared t to the minus 3 to power beta, which is going to give us L minus alpha plus 2 beta times t minus 3 beta. So this gives me two equations. For L, the left-hand side and right-hand side, the exponents should match. So 3 on the left-hand side equals to the minus alpha plus 2 beta. And for t, time, the left-hand side is minus 2, should equal to minus 3 beta. So this means that beta should be 2/3, and thus I can just substitute it in the first equation. So 3 equals to minus alpha plus 2 times 2/3, which is 4/3. So alpha is going to be minus 5/3. So interestingly, we get this relation EK in the inertial subrange should be C constant, a dimensionless number, times epsilon to power 2/3 times K to power minus 5/3. This is a very famous equation in turbulence, and it's known as k to the minus 5/3, or sometimes just 5/3 law or rule, Kolmogorov rule. And it shows the relation of the energy spectra in the inertial subrange with this wave number, which is very kind of much studied. So this C is sometimes called universal Kolmogorov's constant. And this has been studied a lot in literature and also in many experiments, DNS, and a lot of codes try to, when they want to test if their turbulence works well, they just look at the energy spectra, and then they just see whether in the inertial subrange the energy spectra is changing with k to the minus 5/3 or not. So one of the things that you can do also, they have been so many measurements, and this kind of matches with a lot of measurements that have been done. So one of the things that you can do is you can plot energy spectra spectrum. And so what you can do is, for example, you can plot EK over epsilon 2/3, or there are other ways to plot this, but this is a simple one. And then here you can have a non-dimensional thing like K times Kolmogorov microscale. And then if you plot these, you are going to see some spectra that would look like this. And then depending on the Reynolds number, it's going to be different. But one thing is interesting that most of them kind of match at some point. Which is kind of the inertial subrange. And also, the more important thing is that if you plot this in a, say, logarithmic scale, you will see this k to the minus 5/3 law has been applied a lot in the literature. And this, if you put it in the logarithmic, say, scale, and let's say here we have, this is 10 to the minus 2, and then here we have like 10 to the minus 4, so something like this. If you put it in that scale, then here you can get this minus 5/3 line, where the slope of this should be minus 5/3, and it kind of matches with this theory that we made. So this shows that in the inertial subrange, which is somewhere in the between, so this is like the this part is like energy containing range, the large scales, and then here we have like the energy inertial subrange, and then here we have like dissipation range. So in the inertial subrange, you will see that these kind of will kind of obey this minus 5/3 rule most of the times, okay? And here, these different curves are for different Reynolds number, and here is Reynolds number is increasing. So if you increase Reynolds number, you will see that this match becomes better and better, because this is one of the assumptions of the K45 theory, that you need to have a kind of infinite Reynolds number so that you have this separation of scales. And then, so in that range, you will have a better match with this minus 5/3 law. And again, a lot of codes, especially numerical codes, when they want to test your turbulence schemes, this is what they do. They just plot this energy spectra, and then they look at how their energy spectrum behaves in the inertial subrange, and whether they can predict and they can show this minus 5/3 law. And this has been studied a lot also in experimental studies, like for pipe flows or for gas pipes or high Reynolds number flows, or atmospheric flows as well, and oceanic atmospheric flows. Okay, so let me wrap up what we talked about today. So today, we talked about this Kolmogorov's hypothesis, or Kolmogorov's theory. It's kind of one of the most famous ones. Famous theories in turbulence. So we try to find the characteristic length scales, time scales, and velocity scales in different ranges of turbulence. So the first one is energy containing range, which is kind of large scales. So we said, okay, let's imagine an eddy with a characteristic length scale of L, where it's going to be about 2 pi over Ke, where Ke is the energy containing, the wave number with regard to the energy containing range. And then we found the tau L, Tke, epsilon by some dimensional analysis. And then we described the assumptions of Kolmogorov for his theory. So one of them is that as tau decreases, as L decreases, U and tau also decrease, or tau decreases by increasing K. Then small scales are independent of the geometry, so we have some kind of local isotropy. And the most important, one of the most important assumptions is that we have this separation of scales between the large scales and small scales, or in other words, we have this high Reynolds number. And so we have a clear inertial subrange where we don't have any energy production or energy dissipation in that. And then we define this Kolmogorov microscale, where 99% of dissipation occurs before that. And then we did this dimension analysis for the dissipation range. And for dissipation range, we know that the only important parameters are new: the dissipation, the viscosity, and epsilon, which is the dissipation rate. So based on that, we showed these the Kolmogorov velocity scale, Kolmogorov macro scale, length scale, and Kolmogorov time scale. And also we showed that the tau L, the time scale of the time scale, and also the length scale of the large scale over the time scale or the length scale of the small scale is kind of proportional to the Reynolds number. So the ratio between the large eddies and macro scale eddies or small eddies, the size of the largest eddies and the smaller eddies, the ratio between them is proportional to the Reynolds number. So this is another definition of Reynolds number that you can make. And then we went to this inertial subrange, and in the inertial subrange, we see that the energy production is about 0, and also energy dissipation is zero because of this separation of scales. So we can neglect, if you want to do a dimension analysis for that, we have to neglect nu because we don't have any dissipation here, and also u square and L are also not important here. They're scales of the largest eddies. So the only important parameters here are epsilon, which is dissipation rate, and also the k itself, the wave number. So based on that, we estimated Ek to be a function of k and epsilon, and then using some dimensional analysis, we got this very famous rule, or k to the minus 5 third rule, where E, or energy spectrum, is varying as a function of k to the minus 5 third in the inertial subrange. Thank you very much, everyone.